Okay, so hi everybody, welcome to our weekly seminar here at the Institute of Astrophysics. Today we have the pleasure to have Meg, who is a postdoc now with the group of Maria Carisi. And Meg will tell us a bit more about herself now.
Maria was supposed to be here today to hopefully introduce me, but now I get to introduce myself if she couldn't make it. It's nice to finally tell you all what I got up to in my PhD, because I just graduated last year. It's my first postdoc, and tell you what I'm currently getting up to hiding in my office downstairs all the time. I'm quite excited. So yeah, my name is Meg Davis. I use they, them, and she, her pronouns. I'm a queer scientist, and I'm quite proud of that. I work with Maria as a postdoc, and I did my PhD with Jonathan Trump, no relation, at the University of Connecticut. For some more details about me, yeah, I am Meg. I graduated with my bachelor's from Michigan State University back in 2019, and I took a gap year to study low mass X-ray binaries. While I was at Michigan State, I studied everything from neutrino astrophysics through galaxy evolution, extragalactic stuff, kind of did a little bit of everything. I went to the University of Connecticut to get my PhD in 2020. Worst time to start a PhD ever, I gotta say. There, I was a National Science Foundation Graduate Research Fellow, as well as an Institutional Blonder Research Fellow as well. I graduated in 2025. Hilariously, a year ago today, I actually started my industry gig. I left academia for 6 months. I defended my PhD in April 2025, so I actually left academia before I defended my PhD. I won't be talking about any of that today, but if you have questions, especially the graduate students in the crowd, or even the postdocs, faculty, researchers, if you have questions about industry, is the grass really greener on the other side? I'd be happy to tell you all about it. But I'm here, so I think that kind of gives you insight into how that experience went. So take that with a grain of salt. I'm here. I have been here since November. I am seeing new faces today, so hey, nice to meet you. I have been hiding downstairs in my office quite a bit, and you'll see why in a minute, as well as holidays, conferences, all that good stuff. So I'm glad I finally get to tell you all what I get up to, and also advertise that I have so many project ideas. Come join me. Abandon your own work. Come work with me. All right. So for this talk, I want to set some base definitions, real simple. I want to make sure that we're all on the same page. I'm going to chat about supermassive black holes. And so I'm talking about objects, compact objects with masses between 10 to the 5 and 10 to the 11 solar masses. These objects are actively accreting, munching and crunching their way through the gas and dust that accretes around them. I'm going to interchange the word quasar and AGN this entire talk. To me, they're the same thing. To you, maybe not. We can talk semantics later. For the most part for this talk, I'm going to be talking about optical emission, and so I wanted to show you a little toy diagram, a cross-section of an AGN to show you where that emission is kind of coming from, because I don't discuss it again after this. We have the supermassive black hole, and again, these objects are found in the hearts of galaxies, and they have lots of gas and dust around them. They also typically have accretion disks, broadline regions, dusty tori, all that good stuff. The optical emission that we mostly focus on comes from the accretion disk and the broadline region. That's pretty much it. You can kind of ignore everything else for the next 45 minutes or so. Okay. First, I'm going to tell you a little bit about what I did in my PhD, and then you're never going to hear about this again. You'll see why in a second too. So I'm going to talk quickly about the Sloan Digital Sky Survey. That's the SDSS here. Sloan Digital Sky Survey is a spectroscopic survey that started back in the late 90s, I believe. They used these large aluminum plates, humans for scale. That's me. That's my advisor, John. Where they took fiber optic cables, plugged them into the plate. These plates were pre-drilled for whatever targets we wanted to observe. And if you ever wanted to observe a new target through this survey, you had to re-drill the entire plate. The survey was very inflexible. So when it transitioned in 2020 to a brand new era, a brand new generation of SDSS. They actually started using robots, which is awesome. We love a good robot, to position those fibers to get the spectra of these objects that they wanted to study. SDSS studies stars, the Milky Way through the Milky Way Mapper program, but also AGN quasars through the Black Hole Mapper program as well. You can maybe take a guess as to which program I was a part of. I want to highlight that as it transitioned from SDSS 4 to SDSS 5, we finally gained Southern Hemisphere coverage, which is awesome. We were targeting 4 main quasar fields and 2 light fields. So the main quasar fields had a very long baseline, repeat observations. The lighter fields have just less observations, for a total of 1,000+ quasar targets that we could study in depth. We could try to get mass estimates, try to measure kinematics of those inner regions near the AGN, do all sorts of physics. We also developed a brand new streamlined parent catalog, which was awesome. And someone had to do all of that work. And you're never going to guess who did that. Me, for 2 years of my PhD. No papers, nothing else about it. I just did critical survey work for 2 years of my PhD. This is a field map showing you exactly how our fields in SDSS 5 work. These are actual targets, real AGN, both spectroscopically verified AGN and also candidates that we've never observed before. This is one of the southern field, Chandra Deep Field South, the first time we ever got observations of this field. And I plotted those. I handpicked the targets. I made the robots move to those targets to get some of these beautiful spectra. I never used the spectra. I just helped make it happen. And this talk won't feature any work that comes after that, because now I actually get to play with the data now that I'm a postdoc. I've completed my PhD. Now I do get to play with some of that work, but y'all won't hear about that today. But I wanted to tell you all about it because it's important to share some of the work that we've done, even if it doesn't make it to a paper. It's still critical, right? So most of my talk today is actually going to be about binary supermassive black holes and how we can detect them through massive surveys. So first, let's talk about how they can form, how these systems form. They typically form through galaxy mergers. Here I have real images from SDSS of what we call dual AGN, okay? They have those active nuclei, and as we move through the photos from left to right and from top to bottom, the nuclear separations are decreasing, these galaxies are merging, and we actually get to see this process happen over millions, if not billions of years, which is quite fantastic. At this point, they are not gravitationally bound, okay? And for reference, that's kiloparsec to parsec scales. Through interactions with gas dust and stars, they can wiggle their way down to parsec to subparsec scales and eventually become gravitationally bound to each other through, again, millions, if not billions of years. The typical toy model that we use to imagine these objects when they are gravitationally bound to each other is, earlier I showed you that cross-section of just a single AGN. You can now imagine that there are 2. We have mini accretion disks, a larger circumbinary accretion disk that surrounds all of those, both of those objects, and then streams of material onto those mini accretion disks. Quite interesting, quite complex, all wonderful science. So finding these objects will, of course, have broad implications for many areas of science. Gravitational wave physics, these are expected to be the source of gravitational wave background, and individually as the loudest gravitational wave sources. Of course, for black hole seeding, growth, and evolution, mergers as well as accretion may play critical roles in supermassive black hole existence and growth, and as, of course, galaxy evolution. If we find these binary pairs, that means that the galaxy, maybe millions, if not billions of years earlier, had gone through merger. Which is, there's a wealth of science when we find these objects. The issue, again, we're talking photometrically, optically, is that we have hundreds of candidates and no full confirmation of detection. I'm going to tell you why. So first, let's talk about single AGN. Here I have a plot, an optical light curve of an AGN NGC 5548, and you can see that it is variable. Active single supermassive black holes, these AGN, these quasars, are intrinsically variable. We typically ascribe that to thermal fluctuations in the accretion disk. We typically describe that as red noise variability, and there are several ways to describe red noise variability and quasar variability. And I'd like to note that while I choose the damped random walk, it's not perfect. Everyone has their favorites. There's also the damped harmonic oscillator and the karma processes. Many models to choose from. The easiest for me to use to model and then tie back to quasar parameters was the damped random walk. Yeah, so the damped random walk has two major parameters I just want you to remember. That's the structure function, and that's akin to an amplitude, so the changes on your y-axis, and the damping timescale, what can drive the variability back to some sort of mean. It's part of the damped part of the random walk, which is kind of akin to a period. I'm using terms that also kind of relate to binary signals because we'll see that this causes confusion. Okay. So when we're looking for binary supermassive black holes, what we're actually looking for are periodic signals. Binaries can produce periodic signals through the Doppler boost method. So when the when the black holes are moving at significant fractions of the speed of light, that's close enough. You can produce periodic signals through the Doppler boost. And we can see this in a real light curve of a binary supermassive black hole candidate, PG 1302-102. There are a million and one ways in astrophysics to create periodic signals. There are other ways we can physically make periodic signals as well with binaries, but we mainly focus on the Doppler boost. Okay, so single AGN are variable, and we're looking for periodic signals. And we have lots of candidates, no confirmed detection. It's my favorite time of the talk. So all of you who are falling asleep, time to wake up. It's time for you to participate. We're looking for sustained periodic behavior. And here I present you with two I-band optical light curves. One of them, or both of them, or neither of them are actually periodic. One, or both, or neither is not periodic, and it's just quasar variability. So you have four choices. Could it be the left is periodic? Could it be the right that's periodic? Both are periodic. There's an actual periodic signal, or neither.
I say neither.
Neither. Okay, we got neither. How many say the left is for sure periodic? Okay, how many say the right for sure periodic? Look at that. Both. Neither. Okay. I'm so sorry. Shout out to the back row who did that, get that correct. So maybe you can see the issue. We're searching for your periodicity, even by eye. This is a difficult task. And a lot of our detection methods are failing. We're getting a lot of false positives. Thanks for participating. So why can't we confirm them? Again, we're looking for sustained periodic variability, sustained periodic signals. There are other ways to create periodicity with these objects that is maybe not sustained, but we're looking for sustained. The binary signal should not really evolve over our lifetime, okay? But if you look for periodicity in AGN light curves, you're gonna find it. And it's not always binaries. But yeah, those single quasars, they can trip you up. So that's the problem that we're dealing with today. So I have another question for you. Is there hope? We can't do it by eye as a group. Some of the smartest people in the world are here in this room and on Zoom. I see you too. Is there hope? Do I have a job?
Yes.
Yes, thank you. Someone, anyone, please. I hope I have job security at least for a couple more years. Of course, there's hope. And hope comes in many forms, but in this case, it's the Vera Rubin Observatory. I have exciting news about Vera Rubin Observatory as of last night, which is pretty cool. I can't wait to tell you about it in more slide. But for now, I'm going to give you some statistics to show you that the problem, we have hope now because of Rubin, but the problem is still going to be difficult to solve. Finding binaries of this. Rubin is expected to conduct its legacy survey of space and time, that's LSST. It is going to have a 10-year baseline, depending on what part of the survey and what field the telescope was pointed at. The cadence could be less than a day, multiple visits per night, all the way up to 3, 4, 5-ish days, but roughly 1 to 3 days is like the average for visits. We're expecting 20 to 100 million AGN. What a wealth of science we're going to get up to there. We can expect hundreds to thousands of candidate binary supermassive black holes. That's based off of estimates from current surveys, like ZTF, CRTS, other periodicity searches. And it's going to produce 20 terabytes of data every night for 10 years. We are firmly in the era of big data. How terrifying. We need fast detection methods because let's take a look at those numbers again. We have 20 to 100 million AGN to sift through, and we're looking for hundreds, maybe thousands of things. It's kind of like a needle in the haystack the size of the universe kind of problem. If our detection methods take 1 minute per object to determine whether or not it's periodic, that's still 100 million minutes. Oh, can be done, of course. We'll be waiting a little bit. We can procrastinate while that's running, right? Okay, the really exciting thing about Rubin. Rubin, it was being built down in Chile. It was finally completed construction early last year or the year before. It's been through its commissioning phase. The camera that's the size of like a small SUV has been installed. Rubin's going to revolutionize the field. How exciting. Cool, yay. For the first time ever last night, Rubin turned on its public alerts. Rubin is looking for anything that changes in the night sky. And in the first hour, it alerted the public 64,000 times. If there are 64,000 objects in the first hour of it being on, it changed from its last observation. Things that we can follow up with other observatories, things that are cool and transient, maybe things we've never even discovered or even thought about before. And here's just an example of one of the brokers. That was the first time SDSS actually caught a couple of these through its new Target of Opportunity program. And there are many ZTF, there are many observatories across the world who've been waiting for these. This was one of the final steps before survey start. And Rubin is now expected to turn on. Hopefully within the next month or two, we'll see whether or not they adjust the maintenance period. This is really exciting. We're about to experience astrophysics in a way we never have before. It's pretty cool. Job security for all of us. Right?
Sorry, Michael, ask you, what triggers an alert?
Huh?
What triggers an alert?
Yeah. Mostly, so it's mostly difference imaging. Yeah. And you can see that these are like the last 3 observations, and you can see what probably triggered, like on this one is actually these last 3 objects. Is okay, maybe we got a little brighter and then suddenly didn't.
These are the real
These are
within the hour.
Yeah. Yep. And down here, something was there, it disappeared, oops, and it came back.
What is like I mean, I guess also something that's
Oh yeah, that's so there's actually a delay. I lied to you. It's the public alerts actually got released an hour after they were taken. Because the US government especially has to go through and verify that there are no secret spy satellites and other government secrets in these alert streams. The Rubin leadership had some very interesting meetings with people who had their voices masked, their faces masked, who were meeting in an undisclosed location, government officials who they had no idea who they were, but they were very important and they had to be talked to. It's a whole thing. Many stories. But yeah. It was a huge crisis for a little bit of time because Rubin was going to catch all of the satellites. Every single one. within its coverage, of course. And that was an issue, and they thought hard about it. Sweet. They do some pretty interesting post-processing on the images as well to try and get rid of those satellites as well. So, yeah. Okay. So the other part of my PhD, the other 3 years of my PhD was focused on answering these questions. How can we prepare for Rubin? How can we triage single quasars from the binary search? Are there any types of quasars that give us trouble? And what can we actually reliably detect? What types of binaries, what types of binary signals, so on and so forth. As with most things in life, you have to fake it till you make it. So I had to fake a bunch of data until Rubin came online. That's what I did. My first paper, I simulated millions of quasar light curves over broad ranges of quasar properties and broad ranges of binary properties. So broad ranges of quasar properties, as in redshift, masses, luminosities, binary properties, as in amplitudes, periods, signal shape, because not all of them are looking for periodic behavior, but not all of them are going to be smooth signs. Phase as well. So I did that by choosing a variability model, but I can swap that out if anyone else has favorites, other favorite variability models. I construct a periodicity model, combine the two, and then apply observables, seasonal gaps. We lose 30% of all data due to weather. I resample the light curves based off of the error of LSST itself, so on and so forth, as realistic as we could possibly get them for being simulated. And then we threw a bunch of detection methods at these light curves to see what sticks. These are examples of just simple sinusoidal curve fits. I'm talking 3 lines in Python, SciPy curve fit, and then later on like LM fits. Really simple. Fit it with a sine, see what we get back. Mostly as a test, and a testament to astronomers will fit anything with a sine wave, even if we shouldn't be. How bad does it get? Something we want to investigate. So here's an example of a fit to a single isolated quasar light curve, as well as a binary quasar light curve. So, bless you. You're welcome. So, simple sinusoidal curve fits, basic parallelization. At first, I could fit almost 10,000 light curves per minute. Okay, this means we could use this method to triage, get rid of things that for sure aren't periodic, using like the chi-squared and other statistics, before applying more expensive fits, the Bayesian curve fits from Wood et al. 2022, which take 14 minutes per light curve. Okay, this could be used as a first step. When I revisited the code for my second paper, we got up to 50K per minute. Pretty cool. Most methods take a minute plus per light curve. So this is ripping through a lot of data. And that's the goal for most of my detection methods, is to make them as fast as possible, while also studying what do we trade off. What do we lose when we try to make these methods faster? And how can we use them to triage and gut as much data as we can before applying more computationally expensive and maybe statistically robust methods. Okay. In my second paper, oh no, I lied. This is how they formed, in case you're curious. We could actually, if the light curve had a true binary signal in it, we could actually recover the binary phase in the period pretty well. So this is a plot of parameter recovery. That parameter recovery definition is down here at the bottom. It's what the fit returns minus what we put in, divided by what we put in. So what we want to see are nice sharp peaks at 0, as tall as we can get them. And we see that for period, the black line, as well as phase, the orange dashed line, or dot dash. And we see that their phase and period quite well recovered, but it really struggled with variability amplitude, or with the amplitude of the binary. So that broad blue dashed line. And that was absolutely because of the quasar variability. Those structure functions, those changes in magnitude, caused way too much confusion with the binary signal amplitude. We couldn't recover what we put in. What's really cool about this method, and what I want to try and get from all of my methods, is false positive rates. And then in terms of those quasar and binary parameters, we had to make up a definition for a false positive rate. So we had to choose a good fit with a relative chi-squared. Reasonable fit returns on the amplitude and the period. And this is what we got. It turns out, if you look at both the mass and the luminosity of quasars, with this method in particular, we get a high false positive rate that correlates mostly with luminosity. There are stars on this plot showing where some real candidates lie. Maybe around 40 or 50% of the quasars that fall into those boxes are returned as false positives. So maybe we don't trust those as much, and we need to follow up with more robust methods, those candidates. So that was my first paper. And yeah, we were able to give general recommendations for Rubin. My second paper focused on, okay, all of that recovery in terms of survey design as we changed the cadence. I'm so sorry, the yellow looks atrocious. So DDF just represented like one observation every night, bless you. Wide, fast, deep, that's what the main survey is called. This is every 3 days, every 7 days, every 10 days. And then you can see how the baseline moves across the bottom here. The 10-year baseline of LSST. What happens if we can combine data from other telescopes, or maybe Rubin gets extended 20 years, that'd be pretty cool. What happens to our results as all of those things change? What matters more? Is it the cadence or is it the baseline? Does anyone have a guess? Cadence or baseline? I'd tell you no wrong answers, but you'll see, huh? This is true. Also depends on what method. For this method in particular, baseline mattered more. We have that false positive rate, and we have a recovery rate, this time for the period. We have the baseline on the x-axis, and each point, each different color represents a different cadence. So you see on both plots, the points are clustered at every baseline, so the cadence doesn't matter as much. But we definitely see as we move across baseline, we see a very obvious trend. I also tested out whether or not host galaxy contamination mattered for these results. Real basic results, they increase the false positive rate and slightly decrease the recovery rates. Contaminating the light curves made everything worse. Who'd have thunk? Yeah, that's pretty much it. Life may be better in color, periodicity searches maybe too. Most of the results I just showed you. This is newer work that I was doing at the tail end of my PhD. It's not published yet, but maybe one day. I was using I-band magnitudes only, single band light curves. What happens if we expand to all of the Rubin filters? Could that give us an advantage? Maybe. Also using a bit more computationally complex methods as well, like periodograms. And here are examples. So what's happening here? There's a lot happening here. Is a GIF. Love a GIF. If you say GIF, I am judging. Here in the top plot, I'm showing you it's actually the same light curve from the previous slide as it changes in cadence. So the lines get super thick. That's like pretty much one observation every night. And then the lines slowly get a little less thick. It's actually thinning out. There are less observations. Okay, so that's what's happening. In the top, you can see as the cadence changes that the single band periodograms also change. The single band periodograms may work for some filters and may not for others. This gray line shows you exactly where the injected binary period is. And for some of the light curves, depending on the filter, the periodogram can absolutely pick out that binary signal. But for other filters, the quasar noise confuses and would actually have a greater power in the periodogram. And if we actually combine all of those, we may actually get better results regardless of cadence. That's really what I'm showing here. This is still mostly preliminary work because, again, I left academia in the middle of this project, but we were still seeing contamination and then false positives with this method because I cherry-picked a beautiful example here. We also investigated baseline. Hopefully You can see that as baseline increases, we add more data over the years. It becomes very apparent that we can pick out that binary state, which is nice. And again, this was a beautiful cherry-picked example with a strong binary amplitude. We're still expecting false positive rates around 40% from preliminary results. And those follow-up results would also investigate quasar properties and and binary properties, how the false positive rate changes with those. I did mention, I believe, in my abstract that we're working on machine and deep learning methods. I didn't want to bore you with all like the model architecture, but we're exploring both traditional machine learning, so real basic out of the box, like scikit-learn random forest algorithms, all the way through 1D, 2D CNNs. We're taking a peek at it all. Also maybe some vision transformers. We're going to see if we can treat the binary detection problem as a binary classification machine learning problem. Again, testing all those methods. And this is a real example, fresh off my computer this morning, of a traditional machine learning trying to do classification work. Just really looking for, is it periodic? Is it not periodic? So single binary. This is a confusion matrix. Ideally, what we'd love to see is a 1 here for 100% and a 1 here for 100%, that the predicted labels and the true labels match. But what we are seeing is that for the most part, it can separate out single quasars. So it's a reduction in false positive rate. But it's struggling with properly classifying binaries. Hilariously, ran in 20 minutes. This pretty much blows most of our detection methods that we currently have out of the water. For the reduction in false positive detection, so the singles being classified as binaries, and actually properly recovering over 60% of the binaries, which is impressive because this is all the default settings on our random forest algorithm. So maybe if I fine tune, make it a little better. Or with the more expensive models where we had to feed it more data, we'll see some improvement there too. Okay. So yeah, what's next is pipelines. I am the periodicity search task force lead along with Maria for Rubin. So we have to take all of these detection methods. There are about 3 other detection methods that I didn't even show you that I've worked on, as well as a slew of other methods developed by our colleagues that we now get to inject into a pipeline, use all of these results. Okay, this method works for these types of quasars. This method works better for the other type of quasar, or a different type of quasar. Stack them all together, try and create reliability profiles or just some metric that says, okay, we can trust this candidate this much. That's what we're working on. And I'm quite excited about it. So finally, the final question, hopefully some of you are thinking this in the back of your head, is what's going to be the smoking gun? What's going to be the thing that's going to confirm binary detection with Rubin? And I want to answer this as honestly as I possibly can for you, so that way you walk out of here knowing where most of our field stands. Yes. There's one. Sorry. And that's because this is going to be a multi-wavelength. So I've been talking about optical photometric searches. I mean, with an optical, there's also spectroscopic searches, of course, too. We can probe other areas around the system. We can take a look at the jets. We can take a look at the deeper into the broadline region, the dusty torus. We can also look at gravitational waves. These are supposed to be emitting gravitational waves. We should have continuous waves from these objects. That's going to be really important. Rubin's absolutely going to help. We're going to have more candidates. And through all of our detection method testing, we're actually going to have hopefully some reliable detection methods we can trust to a degree for certain types of quasars. But truly, it's just going to take some time. We can, as I showed you with baseline, as these detection methods, we use these detection methods. The more data we get, the more we can trust our results, the more we we better recover our binaries as baseline increases. So it's gonna take time. Innovation and collaboration too. It's not a one person kind of thing. So yeah, I'll leave you there. I see sleepy faces. So in summary, in my PhD, I simulated millions of flight curves, tried out some detection methods. That's what I'm currently doing in my postdoc as well, is testing all those periodicity detection methods, new ones. No one has ever applied machine learning to this problem in this way as a classification problem. So we'll be the first to do that. And survey design implications. As the cadence changes, what on earth are we gonna get? I'm unbelievably excited about Ruben. I'm also really excited about Roman as well. Yeah, it's a really good time to be an astronomer. So thanks. This is my stand-up routine. Like, this is like my favorite thing to do, is to share my science with people. Nothing better.
So any question here online? Yeah.
Go ahead.
Yeah. There was nothing.
Agro.
Okay. Can you give us this stuff? Can you go to the two projects where we had the exercise project?
Which one?
The exercise that was a question for the audience.
Ah.
Yeah.
This one.
So I was looking on the x-axis and so these are two different mechanisms that produce this seemingly distributed by art. And so I see that you're doing something periodic thing, but it's induced through like different physical mechanisms, right? The one is like from the binary, the rotation, and the other is like rotation property equation. But I see that the time scale in which the thing varies is completely the same. So it's usually the case, or I would expect it to be completely different time scales. So I would expect the rotation to be like, I don't have any method like myself, what would I expect, but it wouldn't be the same. So is it fine tuned here or is it usually the case?
This was a pretty specific example to cause confusion for the audience, not gonna lie. What we expect for quasar variability is the damping timescales on the orders of hundreds of days. The binary period can be anywhere from tens of days to 15 years. So the binary period could be all over the place. In truth, this was a very specific example. But
This confusion is very small. Right?
Yeah.
So on the other cases, you have a good method to know if it's the one or the other, right? Because the time scale is completely different.
to a degree, it depends on how long we've been observing these objects. We need to be confident that we have detected the signal, so we need at least 1.5, 2 times the base, 2 times the period of what we're looking at as the baseline, right? We need to be confident there are at least 2 cycles,
Yeah.
or at least 1.5 represented. So if we're looking at 10-year periods, we need to observe this object for 15 years. We currently don't have that for a lot of objects, and that's why Ruben is already going to give us a 10-year baseline no matter what, in combination with CTF, CRTFs, and all previous observations. It's really going to revolutionize. Those are good questions, though. Timing is everything. That was the title of my thesis, and timing, those timescales matter for investigating these objects.
Like statistics of how frequent it's possible. Like what is the most probable period per binary or so you can model these things?
They can be modeled. We have limits from gravitational wave searches, but we have not officially confirmed detection of these objects, so we don't have.
Yeah.
It's theory and limits. You had a question?
Yeah, thank you for the talk. Considering the binary system, so the multi-messenger astronomy, if you consider VLPI here, and you consider OJ287 also, it has a lot of data, and we expect that there is a binary in that system, which shows periodicity of 10 years, I think.
Yeah.
And there is a light curve variability also seen in the light curve.
Yep.
So can we extend this analysis to jet precision also, because there is a theory that if the binary passes close to the central supermassive black hole, the jet can wobble.
Yeah.
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 So can we expect that in other systems also? And what can be the parameter space where, because there is also one theory which says that if the binary is very close, if it is very close to the supermassive black hole, it can disrupt the accretion disk itself. So there is no jet, so there is no precession. So what do you think about this?
I'm not as familiar with investigating the jets, forgive me. Any and all extra observations and other wavelengths that also confirm periodicity, whether it actually could be wobbles, like lensitarian precession, all that good stuff, helps. We should be observing these things in tandem over multiple wavelengths. To me, that what's going to end up confirming these detections is some sort of EM detection, whether that be through the jets, whether that be optical. I'm hoping it's optical, it'd be nice for me. And the gravitational wave, continuous wave detection. Those two hand in hand, fantastic. The issue as we start to look at just using EM data is there, like I said earlier, multiple ways to produce periodic data with just a single supermassive black hole. Those aren't typically sustained over long baselines. So with that example, 10 years, sustained behavior for the most part, gives us a confidence boost. But yeah, we have to be careful with just EM detections.
Hey, in your the machine learning results that you saw that were
Yeah.
exciting. So one thing I was wondering, and in fact, what I find amazing is the very low force quality rate.
No,
It's very
right?
important for
Right?
But one thing I was wondering is, are you using the full 10-year life curve, or okay, how long is the?
So I was feeding 5 years and I have tested 10. But there's a cadence applied and I'm using the equatorial fields, which also have season gaps. It's not talked about in my talk at all, so I want to save time, not bore you all to death. But I'm using two representations. I'm testing the raw time series, the sequential data, as well as image representations.
All right.
Yeah, through like DMDT images. Every unique point, you can create image representations. For the traditional machine learning models, they're going to get both to see how they perform. And then we're developing these deeper learning models. Some of them are better for images, with maybe 2D CNNs. So we'll use it on the images, and maybe a fully connected neural network or 1D CNN on the sequential. Maybe combine them both.
So these impressive results are for the 5-year time span? Okay.
Which I can't wait to dig into these. So I mean, for every one of these boxes, I now get to dig into, okay, what quasars are in these boxes? I can't wait. Do you know how excited I am to see what on earth is in this box, what remained, and also what on earth is tripping up the binary classification? I can't wait. Maria's excited too, but she actually hasn't seen this yet. So I'm actually excited. Yeah.
If I may ask one more question, please. When you saw the first positive rate where you have the luminosity versus mass, so it looks like there is a very strong bridge of this density. So is this because in the model there is an assumption about the electron fraction? Okay.
It's the underlying parameter grid. We also have to deal with limits, magnitude limits from Rubin. This was a continuous parameter grid. This was not based on like quasar luminosity functions. In my second paper, we actually updated to reflect quasar luminosity functions and number densities for expected.
And this mass is the sum of the masses of the binaries or of the?
Yes. In this case, because it's a false positive rate, it's actually the single black hole, masquerading as a binary. But if you see a mass again, but in terms of the binary, it'd be the combined mass. And then the luminosity, if it were a binary, is actually the luminosity of the secondary. It's the secondary sweeps more luminous. Good questions. Good eye.
Question then. Okay.
Thanks.